Good evening. Tonight's video is about curve sketching, particularly the extension 1 component of it. What makes it different is that we're dealing with what are called rational functions. Rational is a fraction, hopefully you remember that. So a rational function might look like, for example, y equals x squared minus 4x, minus 5 divided by x squared, I'm not sure what happened there, divided by x squared minus 9. Now, I want you to pause the video in a second, and I want you to think about what the important characteristics are for sketching this curve, and I'd like you to even just try doing it. Doesn't matter if you're wrong, just try and go through what you think are all the key characteristics, and then try and have a go at actually drawing it before you hear me say anything else. So pause now, and then I'll be back. Okay, I hope you've had a go. So the important things often remembered by people in an acronym called Dr. Isaac. They stand for domain, range, intercepts, symmetry, asymptotes, this one stands for anything else, which we'll talk about later. Oops, that's roughly how you spell it. And then the last one stands for calculus. Okay, so we're actually going to do it for this curve here. So let's move on to a new slide. Okay, so firstly, domain, D. Clearly I can't divide by 0, so my domain is going to be x squared minus 9 can't be 0. Oh my god, I'm having a shocker. Which is the same as saying x cannot be equal to positive and negative 3. So if I kind of start putting stuff on the diagram as I go, means I've got my asymptotes. Oh, isn't that nice? I've already done the A. At 3 and minus 3. Then I could talk about range if I wanted to, but in fact for this one, it's not really easy to talk about range at this point. So let's skip that for the time being, and let's go to I for intercepts. So hopefully you'll all remember that if I'm going to make this a 0, which is a fraction, the only way a fraction can be 0 is if the top is 0. So I get that, and that's x minus 5, x plus 1. I really hate these styluses. If anyone has a better solution, please tell me. So I get x equals 5 and minus 1 are my solutions to the intercepts. So here we go. I can chuck some points on the curve. So there's one there. That's where I'm trying to draw. And it's doing things that I don't want it to do. So there's one there at minus 1. And there's one here at minus 5. The next one is symmetry. So symmetry stands for odd even. Is it odd or even? Correct. It is neither. For a number of reasons. You could try subbing it in. You could just look at it and say there's even powers and odd powers. So it can't be odd or even. You could do a lot of things. So A, asymptotes. Can't do anything there. A also stands for anything else. So one of the things that fits into the anything else basket is what happens in the sense of limits. So for me, what I want to think about are the limits as x approaches minus 3 from below, the limit as x approaches minus 3 from above, and then the same thing for it approaching positive 3, and then later I'll also do infinity. So let's deal with the negative 3. So to do that, it's just a matter of picking a value slightly less than minus 3. So I might start by writing this in factorized form. It's a bit easier at that point. So you say, what happens when x is slightly less than -3? So I'm going to highlight the things that will be negative. So slightly less than -3. So this will be negative, because it might be like -3.1. This will be negative. So I get two negatives on the bottom. This will be negative, and this will be negative, which means that there's two negatives on the top, two negatives on the bottom. So it's going to be positive. So that means that my curve, that I'm now going to change to drawing in grey, up here looks like this. Right? Because if you imagine, and now my slide is getting ridiculously overcrowded, so while I talk I might rub some stuff out. If you imagine what's happening as x approaches -3, I'm effectively dividing by 0, or something very close to 0, because of this section here, right? Sorry, not that one, this one. So I might as well be dividing by 0, which means I head off to infinity. So now, what about from -3 from above? So a number slightly bigger than -3, so maybe -2.9. So what's negative? That's negative, that's negative, that's negative. So 2 on the top, 1 on the bottom. So it's minus a negative number, so it's minus infinity. So my curve looks something like that, which means that my curve has to do basically that, right? Or something like it. At this point, you kind of think about drawing in pencil. In fact, I could have extended to that over there. And then I might just have to change it depending on what happens with my calculus. So then I do the same thing for what happens when x... Oh, damn, sorry. Let's just get rid of those. And let's draw in again. This is probably my best video yet. I could also put in what happens when x equals 0 at this point. It's 5/9, right? So it's going to go through there. So when x approaches +3, slightly smaller, so let's say it's 2.9. So that's negative, and that's negative. So it's positive, as the curve looks like. So it's probably going to do something like that. Now, hopefully you're all thinking to yourselves now, where's my inflection point? Okay, is there a turning point? Is it a horizontal inflection? What's going on? That's a good question, right? We'll find that out soon. And then, last of all, I've got to remember this undo thing, it's really annoying. What happens for 3.1? So hopefully it's fairly obvious that the only thing that's negative is the x minus 5. So it gives me this, basically. Okay. So now, the next thing is calculus. So I do y dash, and I was a fool because I didn't do this beforehand. So I'm going to pause, and now I'm going to resume, and I'm going to correct my mistake that you guys have probably been looking at for about 5 minutes now, and going, Dr. Emmanuel, you are a fool. And you would be correct. This here means the root is at 5 and not -5. I will explain in a minute why I was getting nervous as I was talking, but just kind of winging it and hoping something would happen to make it obvious why I was wrong. But yes, okay, I'm going to skip over the calculus for now because this video is already a bit long and we'll do the calculus tomorrow. But the last thing I want to talk about is the limit as x approaches infinity of this stuff here. Now, basically what's happening as x gets really big, when you square x, it gets really, really big. And compared to x squared, x might as well be nothing. And similarly, 5 and 9 might as well be nothing. So all you really need to look at are the 2x squared terms, and I can tell you that the limit is 1. Now, I want you to just think about that tonight, and I will prove it to you in class tomorrow. But I want you to think about why that might be. So what I've got is I've got a horizontal asymptote at 1. And that's basically my curve. The things I need to check are, where is my inflection? Because there has to be one there. We can see that it goes from concave up to concave down through this region. Also, is there a turning point here? You should be able to answer that based on this stuff, but is there a turning point here? Okay. Are there many turning points? What's going on? So I'd like you to think about that tonight. And it's worthwhile as well having a go at trying to sketch this one for me tonight. Okay, using the same kind of approach. And we'll talk about all the various things that we've gone through here, including all my stupid mistakes, in class tomorrow. Here comes the photo. Okay, see you period 2 tomorrow.